Everyone, excuse me. Let's start this section by learning how to name polysubstituted benzenes. Polysubstituted means more than two substituents. So let's see, in the first one we have three substituents. We do not try to give priority to anyone. Instead, we try to give the lowest number to all the substituents. For example, if you start from here giving 1 to NO2, you can go from 1, 2, 3, 4. So the substituents get 1, 2, 4 numbering. But if you start from here giving this number 1, it would be 1, 2, 3, 4. So substituents get 1, 3, 4 numbers. But if you start from the way it is numbered right now, it would be 1, 2, 4. So that's why we prefer 1, 2, 4. And once you number the ring with the substituents, then you choose the substituents, alphabetical order of the substituents. The B, bromo, would be the first one. So then we will write it as 2-bromo, and then the chloro would be the next alphabetically ordered substituent, 4-chloro, and then 1-nitrobenzene. Okay, so that is how you name it. And let's look at this one. If you number from here, we have 1, 2, 4 for the substituents numbering. If you start number 1 giving bromo, there would be 1, 2, 3, 4. 1, 3, 4. So 1, 2, 4 is lowest order compared to 1, 3, 4. You go by this way. 1, 2, 4, and then out of the 3 you go with the alphabetically ordered substituent, which is bromo comes first. That would be 4-bromo, 1-chloro, 2-nitrobenzene. Okay, and then the next one you can go 1, 2, 4. If you go from here 1, 3, 4, so you pick this way, and then 1-bromo, and then we have 4-chloro should be the next one because the C alphabetically comes after B, and then 2-nitrobenzene. That's how you would name a polysubstituted benzene. Okay, excuse me. And then let's see, you have substituents, but then we can also find out some of the substituents could be incorporated into the benzene ring. What does it mean by incorporated? Remember, we know phenol is benzene ring with the OH group. Now this one, we have a name when the benzene ring have a carboxy group, which is a carboxylic acid, the benzoic acid. Okay, so incorporated name is benzoic acid. And then you give the substituents numbers, giving us the least numbers. Least order of the numbers. Let's say if you number this one as 1, nitro group will be 2. This would be then 2, 3, 4, 5. So we have 2 and 5 for the substituents. But if you go from this side, it would be 1, 2, 3, 4, 5, 6. That would be 3 and 6. So 3 and 6 is a higher order compared to 2 and 5. So we go from this side and then name the compound as benzoic acid. That would be, then you choose the alphabetical order bromo, 5-bromo, 2-nitrobenzoic acid. Okay. Now here we have OH, bromine, chlorine, and out of this we know that the main compound here is the phenol group, OH. And then you give the numbers to these two, giving this number 1, 2, 3 and 4. If you go from the other side, 1, 2, 3, 4, 5. Right? So 4, 5 is higher order compared to 1, 2, 3 and 4. Excuse me. So this would be then bromo, 3-bromo, 4-chlorophenol. And here is an incorporated substituent we have here is the NH2 group. Benzene ring with NH2 is called aniline. Okay, so our substituents are going to be these two. So we give the numbering 1. Number 1 would be here, 2, 3, 4. 2 and 4. So this is ethyl, this is iodo. Ethyl comes prior to iodo, so there would be 2-ethyl, 4-iodo-aniline. Okay, incorporated substituent is given the number 1 position. That's how you name polysubstituted benzenes. Okay, effect of substituents on reactivity. When you have a substituent on the benzene ring, we can still do a electrophilic aromatic substitution, and we need to know where the incoming electrophile gonna go. So in order to do that, we need to know relative rates, like whether we have a activating group or whether we have a deactivating group, and how strong the activation and all that. So we're going to learn that. Okay, so let's say you have a substituent already attached on the benzene ring. Z denotes electrons, sorry, donates. Z donates electrons to the benzene ring. Okay, so let's say you have a compound or you have a substituent that can donate electrons to the benzene ring. We talk about benzene undergoing electrophilic aromatic substitution, meaning electrophiles add on to the benzene ring. So the benzene ring acts as a nucleophile. Nucleophile is a species that is electron rich. So if you have a substituent that can donate electrons to the benzene ring, it increases its nucleophilicity. So if a benzene ring has a substituent that is electron donating group attached to the benzene ring, it's going to be more reactive compared to a non-substituted benzene ring. Okay. Similarly, if a benzene ring has a group, let's denote it as Y, which withdraws electrons from the benzene ring. If it withdraws electrons from the benzene ring, what happened to the nucleophilicity of the benzene ring? It decreases, meaning the reactivity of the benzene ring towards another substitution would be less compared to a benzene ring without any substituents. Okay. Substituents that donate electron density to the benzene ring increase benzene's nucleophilicity and stabilize the carbocation intermediate. Substituents that withdraw electron density from the benzene ring decrease benzene's nucleophilicity and destabilize the carbocation intermediate. Let's look at some activating substituents, meaning that it donates electrons to the benzene ring. For example, NH2 group. So this molecule or this benzene ring with NH2 is called aniline, has a NH2 group. It has a lone pair. Now it gives those lone pair also to the benzene ring, increasing the electron density of the benzene ring. Do you see that? Similarly, hydroxy group, OH group in a phenol has a lone pair, gives its electron and increases the electron density. Similarly, alkoxy group, OR group, right? Oxygen lone pair gives electrons to form a pi bond, and it can be resonance stabilized like this. So these groups, NH2, OH, alkoxy, they are all strongly activating substituents. Okay? Strongly activating substituents donate electrons by resonance and withdraw electrons inductively. Why would you say it will withdraw electrons inductively? Through the sigma bond, it can withdraw electrons because nitrogen is more electronegative compared to carbon. Oxygen more electronegative compared to carbon. Oxygen more electronegative. But their resonance stabilization is more compared to the withdrawal of the electrons through the inductive effect. Because the substituents are activating, electron donation by resonance is more significant than the inductive electron withdrawal. So these are strongly activating substituents. Now there are moderately activating substituents. Now remember the earlier one, we had a NH2. Now this is an amide group, NH. Now we have a carbonyl group and an alkyl group. In the previous one, we had a OR group, ether substituent. Now here, you have oxygen and a carbonyl group. Okay, so these are moderately activating substituents. Moderately activating substituents donate electrons by resonance and withdraw electrons inductively. These lone pairs on the oxygen can also participate in resonance similar to what they did over here. But why they are moderately activating is because this lone pair also busy making resonance with these carbonyl groups. So because of that, it decreases the availability of the lone pair solely for the benzene ring, because it's sometimes it would spend time resonating with the benzene, sometimes it would resonate with these carbonyl groups. So that's why they are moderately activating substituents. Okay, so this is what I just told you. So the nitrogen can participate in the resonance with the benzene ring. You see, gives electrons here, the pi bond breaks and gives 2 electrons to this position, ortho position. This resonance can go around the ring and form another resonance structure having negative charge here. And then this lone pair donates electron to form a pi bond. This pi bond breaks and negative charge comes over here, and then back to the this compound. So the negative charge forms the pi bond here and then come back down here to give us the original molecule we started with. Now, not only this resonance that it would undergo, it also undergoes resonance with the carbonyl group like this. Lone pair, since you have another carbonyl group over here, forms a double bond between this carbon and nitrogen, and then carbon-oxygen pi bond breaks and make another resonance. So the substituent donates electrons by resonance away from the benzene ring. You see here, now the resonance is going to happen away from the benzene ring. It does undergo this resonance as well as this. So because of that, they are activating, but they are not as strong as aniline, phenol, or benzyl ethers. Phenolic, not benzyl, phenyl ethers. Okay. Moderately activating substituents are less active than strongly activating substituents because they donate electrons in two competing directions. Okay. And then we have some substituents, they are activating but they are weak activators. For example, you have an alkyl group or you have an alkene. Okay. Now, alkyl group doesn't have any lone pairs, so it cannot donate electrons through resonance. Alkyl substituents donate electrons only by hyperconjugation. Okay. You have learned about the hyperconjugation in organic 1 when we looked at the carbocation formation. Okay. Aryl and these double bonds, alkenyl groups, donate and withdraw electrons by resonance. Electron donation is more important. So the alkyl groups donates electrons by hyperconjugation and they are activating but weakly. So these are the aryl group. Another phenyl group is an aryl group and this is an alkene group. They donate and withdraw electrons by resonance. Electron donation is more important. They also donate electrons, and because it donates electrons, they are activating but weak activators. And there are some compounds weakly deactivating. Okay, weakly deactivating substituents are basically halobenzenes. When the benzenes are attached to halogens, fluorobenzene, chloro, and bromo and iodobenzenes. Remember, they also have lone pairs on it. All weakly activating substituents donate electrons by resonance and withdraw electrons inductively. You know halogens, if you draw your proper Lewis structure, all of these halogens has 3 lone pairs. That lone pairs, just like oxygen that we saw in phenol, can participate in resonance. And at the same time, these halogens are more electronegative compared to the carbon. So they withdraw electrons also. All weakly activating substituents donate electrons by resonance and withdraw electrons inductively. This is also activating, not deactivating. Because the substituents are deactivating, electron withdrawal is more significant than the electron donation. Substituents are deactivating. Electron withdrawal is more significant than the electron donation. Since they are more electronegative compared to the carbon, so they deactivate more strongly compared to their resonance contribution. So these are weakly deactivating substituents, and these are moderately deactivating substituents. Moderately deactivating substituents can have a carbonyl group directly attached to the benzene ring. Like this is benzaldehyde, aldehyde group attached to the benzene ring. And this is a ketone group, carbonyl and alkyl group. And this is ester group attached to the benzene ring. And this is a carboxylic acid attached to the benzene ring. And then the previous set, when you have halogens, they are weakly deactivating. Now these are moderately deactivating. These compounds deactivate more than when you have a halogen attached to a benzene ring, because they deactivate the benzene ring through resonance. You see how the resonance takes place? Now this carbon-oxygen pi bond can break and give its oxygen to electrons to oxygen, making oxygen negatively charged, carbon positively charged. So the benzene ring pi bond can break and form a double bond between these two carbons and make a positive charge here. So they take electron density away from the benzene ring. So these substituents, when you have a pi bond, especially the carbonyl group next to the benzene ring, so they are moderately deactivating and withdraws electrons by resonance and withdraw electrons inductively too. So withdraw electrons by resonance as well as inductive effect. And then these groups, they are strongly deactivating substituents. For example, a nitro group. When you have a nitro group, so there is an oxygen here and there is an oxygen over here. So you can have two resonance forms with the NO2 group, and all that can participate in resonance with the benzene, but removing electrons from the benzene ring. You see here? Nitro group, and same thing with a cyano group, a nitrile group, a triple bond. So the pi bonds, so these are nicely conjugated. So this can form a double bond here and then form carbon-nitrogen double bond, and nitrogen going to have a lone pair on it. So these are taking electron density away from the benzene ring. They are strong deactivators. Sulfonyl group. You see, these can participate in resonance with the two double bonds. And then protonated nitrogen amine groups. They all are strongly deactivating substituents. All strongly deactivating substituents except ammonium ions withdraw electrons inductively and withdraw electrons by resonance. All of these. Okay. Ammonium ion, this one, cannot have any resonance, but it withdraw electrons through induction, inductive effect. And this is the order of substituents and category whether they are electron donating or activating or deactivating. Okay, so most activating, strong activating groups are NH2, NHR, NR2, phenol, alkoxy groups, and all of these are strongly activating. Moderately activating, these amides and ester groups. Weakly activating alkyl, aryl, and alkenyl groups. This is a standard comparison with hydrogen. And then the deactivating substituents are these groups: halogens, weakly deactivating, and then aldehydes, ketone, carboxylic acids, and esters. They are moderately deactivating, and they are meta-directors. We will see why they are meta-directors. And then the sulfonyl, protonated amine, nitro groups, they are strongly deactivating. Okay. Now, the effect of substituents on orientation. When an electrophilic aromatic substitution reaction occurs on a substituted benzene, where does the new substituent attach itself? And we know if it is just the benzene ring, the substituent can attach to any place because every place is similar in electron density. Whereas if you have a substituent already attached and you want to put another substituent, then we need to figure out whether it's going to go to ortho position, meta position, or the para position. If it goes to the ortho position, you will have a substituent like this. This is the meta isomer and this is the para isomer. Orthopara directors. All activating substituents are orthopara directors. What are the activating substituents? Like OH group, NH2, alkoxy groups, alkyl groups, and what else? So in the list, you can refer to the list that we just looked at. All of those activating substituents, they are orthopara directors. Let's say you start with this toluene molecule. You do a Friedel-Crafts, you do a bromination on the benzene ring. Now it is toluene in the presence of a Lewis acid. And it can either go to ortho position, meta position, or the para position. But since it's activating substituent, it will only go to ortho and para position. And you will see why in few minutes in the next slides. Okay, ortho isomer and the para isomer. Now let's say you have a weakly deactivating substituents. They are also orthopara directors. Okay, so these are activating substituents, weakly deactivating substituents, also orthopara directors. It will go to either to ortho position or the para position. And then the meta directors are going to be all moderately and strongly deactivating substituents. They are meta directors, moderately and strongly deactivating substituents. For example, nitrobenzene. When you brominate nitrobenzene, it would only go to meta position. Okay. Okay, so now let's see if you have a group that is activating group attached to the benzene ring, what happens when it when the substituent goes to these three different places. Which carbocation intermediate is the most stable? Let's say you do this reaction, meaning adding the Y, which is your electrophile, onto this molecule anisole. Anisole has a methoxy group attached to benzene, and this is an activating group. Remember, this can activate benzene ring by resonance. Okay, if it goes to the ortho position, where are we going to have the positive ion? Right next to the oxygen. Okay, so this one, we can draw the available resonance structures for this cation. One is the pi bond here forms a bond between these two, generate the carbocation right there. And then the other one would be gives electrons in the pi bond to form a pi bond between these two carbons, and now you're going to have a plus charge here. Okay, and also one more resonance structure that you can draw here is when you have the positive charge right next to the oxygen, this lone pair can donate electrons to form a double bond, a pi bond between this carbon and this oxygen, like this. Okay, and this is a relatively stable resonance structure. So when the electrophile attached to the ortho position, 1, 2, 3, 4, there are 4 possible resonance structures. The more resonance structures a molecule can have, it's going to be more stable. Okay, let's look at meta position. If this adds on to the meta position, what's going to happen? So you're going to create a positive charge here, and then the resonance structure for this one would be having another positive charge over here. A resonance for this would be giving the pi electron to form a bond here and another one right there. 1, 2, 3 resonance structures. We do not have a substituent where you can directly neutralize this positive charge like we did when we have the methoxy group where we had added the incoming group onto the ortho position. Do you see that? Methoxy group is right next to the positive ion. It didn't happen when the electrophile attached to the meta position. Okay, so that's why it doesn't go to the meta position. Similarly, when it goes to the para position, you can see here, this is the intermediate, and then you can draw another resonance having a positive charge here, and then you can have another resonance having positive charge there. And to this one, we can draw another resonance where the lone pair of the oxygen forms a double bond and oxygen have plus charge. So when the electrophile attached to ortho and the para position, you have 4 resonance structures. And also methoxy group can directly neutralize the positive charge, forming a double bond, where when it adds on to the meta position, it does not have that added stability. So as a result, if you have an activating group, then incoming electrophile will go to either ortho or the para position. Okay. For substituents that donate electrons by resonance, ortho or para substitution forms a relatively stable resonance contributor. So that's why we say that when you have activating substituents, they are ortho-para directors. Okay. Now the same thing, if you have a methyl group, now methyl is an alkyl group, it's going to it cannot form resonance, but it can donate electrons through induction. For substituents that donate electrons inductively, ortho or para substitution forms the most stable resonance contributor. Similar to the previous diagrams that I explained, the resonance structures, you can see here when the electrophile goes to the ortho position, you can draw these 3 resonance structures. Where the positive charge is, one of the resonance structures happen to be right next to the methyl group. So the methyl is an electron donating group through induction. Okay, and if it goes to the meta position, you see here the positive charge is not directly where the methyl group is, but on the other places. One is here, and then the other one is here. In this case, ortho, meta, para position all will have the same number of resonance structures, but through the induction, alkyl group can give electrons to the positive charge to neutralize it, and thereby making the most stable addition would be to either to ortho or the para position. Okay. So for substituents that donate electrons inductively, ortho para substitution forms the most stable resonance contributor. If you have a protonated aniline, you try to put a electrophile on the aniline if it goes to the ortho position. So for this position, you're going to create a positive charge right next where you already have a positive charge. So what's going to happen? When you have 2 similar charges next to each other, they are going to be unstable. So this is least stable resonance structure. Okay, and then you can draw another resonance structure having positive charge here and here. That's what happened when the substituent adds on to the ortho position. Same thing happened when substituent add on to the para position. You will end up having the positive charge, one here, one right next to the nitrogen and one there. When it comes to right next to the nitrogen, 2 adjacent positive charges will make it least stable. When the electrophile goes to the meta position, the positive charge will be not right next to the nitrogen. You see here, one going to be here, other two are going to be one on this carbon and then the other one on this carbon. So it will not create least stable structure as it did with the ortho and the para. So the protonated aniline will be a meta-director. For substituents that withdraw electrons, ortho or para substituents forms a relatively stable resonance contributor. Excuse me. As a result, they would be a meta-director. Okay. Ortho-para ratio. Now let's see here. We are going to do a nitration on toluene. This is toluene. You add nitric acid and sulfuric acid, generate the nitronium ion. And then the ortho position and para position, you get a mixture of that. 61% nitrobenzene, nitro group. On the ortho position, para position about 40%. And if you have an ethyl group, it's about 50-50. Ortho position and the para position. Normally, you can have both of the place, both of these places can get nitrated, ortho and the para. And if you have a bulky group, like tertiary butyl benzene, when you try to do a nitration, this ortho position will be much more hindered. So it will be difficult for the nitro group to attach to this place since there is a steric hindrance. So instead, more of the para position would dominate. Okay. So the size of the substituents affect the ortho-para ratio. I guess I'll start the next session later.